Okay, so how do we actually compute triple integrals? So if we're integrating over boxes, we have Fubini's theorem again. Although your book doesn't call it Fubini's theorem, but essentially it's Fubini's theorem. So if you're integrating a continuous function over a box, then the triple integral is just the iterated integral. Now your book only presents it this way. If you're integrating over a box and your function's continuous, you can actually do this in any order, as long as you change the bounds in the right way. But any order works, as long as you respect the bounds of the integrals. Any order works. And what I mean by that is, let's say we switched dz and dy, we would have to switch the bounds of these two integrals here. Okay. But in any case, for boxes, same thing that we had in double integrals. We just have to compute this triple iterated integral. Okay. But not too shabby. Now, if we're integrating over something that's not a box, then we have to do what we did back in double integrals. So, for example, if we're integrating over a solid bounded by the cone, z is equal to square root of x squared plus y squared. By the way, this is just a sticking point, but this is actually a half cone. Cones are actually almost hourglass shaped. Okay? But the thing that we usually use for ice cream, so a regular cone like this is actually only a half cone, and that's actually what this function here represents. And if you're unconvinced of that, take the level curves like we did in like week 2 or week 1. But in any case, if we're integrating over a region or a solid, okay, that's not a box anymore, then what we have to do is we have to parameterize the solid, and then we have to put that parameterization inside the bounds of your triple integral. So let's go ahead and sort of talk about how we would do that with this solid here. So z is equal to square root of x squared plus y squared. What that's going to give you, again, is just the top half, because it's the plus part of the square root. If you wanted the full cone is actually given by z squared is equal to x squared plus y squared. And then when you take the square root of both sides, you're going to get z is equal to plus or minus square root x squared plus y squared. Okay, but we're only taking the plus here, so we're only getting the top half of our cone. In any case, so we have our cone. Okay, imagine an ice cream cone. Okay, now cones actually do go off to infinity, unlike our ice cream cones. But in any case, we're integrating over the solid bounded by z is equal to square root of x squared plus y squared. That's this guy. And the plane z is equal to 3. Okay, so if we cut this cone at z equal to 3, kind of like what I've already done here, we're going to get our normal ice cream cone, where this circle at the top here is just a circle of radius 3. So imagine that we took our ice cream cone here and we filled it just to the brim. Okay, that's the solid that we're integrating over. Okay, so if we want to integrate over this region, again, what we have to do, since it's not a box or a rectangular box, we have to parameterize this. So we have to give some bounds for our variables. Whoops, I don't know why I wrote z twice. Okay, so since we have the functions of z here, let's go ahead and start with that. So notice that z, if I take a slice this way, z is bouncing from the top part of the plane, which is just 3, and the bottom here is just the cone. Okay, so we have that z is going from square root of x squared plus y squared to 3. Okay, so that's the z direction taken care of. Now, to figure out what happens with x and y, we're actually going to see that we go back to what we would do in double integrals. So imagine we took this cone and we smashed it into the xy plane. Okay, I want you guys to imagine that. Imagine that we take this whole cone, okay, this right here, and we're going to smash it into the xy plane. What do we get? So I'm going to erase this for right now while you're thinking about it. Okay, so if we smash it, you can sort of think about it as a collapsible cup. We're going to get that upper circle on the very top of our cone there. We're going to get a circle of radius 3. Okay. Whoops, and that should be minus 3 right there. Okay. So to parameterize our circle of radius 3, we just do what we would normally do. How do we get the circle of radius 3? Okay, well, let's go ahead and cut it this way. Okay, so if we cut along the x-axis, x is going to be going from -3 to 3, and at the same time, y is going to be bouncing from this to this. Okay, so what's the equation of this top part of the circle of radius 3 and the bottom part of the circle of radius 3? Remember that, well, the equation of the circle of radius 3 is given by 9 is equal to x squared plus y squared. Okay, so if we solve for y, we're going to get that y is equal to plus or minus square root 9 minus x squared. Okay, so the top part here, that's going to be plus square root 9 minus x squared. And then the bottom part here, it's going to be negative square root of 9 minus x squared. Okay. So that would be our parameterization for this solid here, this cone, this filled-in ice cream cone, although only filled to the brim. Okay. So if we want to integrate the function x, for instance, over that region, what we would do is we would set up our triple integrals. We would put our bounds, and I already forgot our bounds. So z was going from 3 to, or square root of x squared plus y squared to 3. And then we're going to integrate, just for an example, x dz. And then for y, our bounds would be our circle of radius 3, essentially. So minus square root 9 minus x squared, square root 9 minus x squared. And then x, oh, let's not forget our differential. And then x is going from minus 3 to 3. Boom. Okay. Now I'm fairly certain that even with x here, this would be a crazy integral, so we'll go ahead and stop there with that. But that's how you would set up a triple integral over a non-rectangular box region. Again, you have to parameterize like we did with double integrals. One thing I want to note, and again, your book, I think, does a pretty good job of doing this. When you parameterize your surface, you can always parameterize it in different ways, okay? And depending on how you parameterize it, that's going to change, your triple integral. Okay. Now, when you're setting up your bounds, it's important to remember that as you move from integral to integral, you should be losing a variable. So for instance, if we're integrating with respect to z, then y, then x, then the bounds on the first integral can only be in terms of the other two variables. And then the bounds on the next integral here can only be in terms of the last variable. And then the bounds on the last integral can only be constant. It's kind of like dominoes in a way. You're sort of chopping off a variable at each stage. Okay. And again, the order does not matter. It's the same idea. So if we were integrating with respect to y first, then the first integral can only have bounds in terms of x and z, or it could be constants, but at the biggest, it can only have the variables x and z. And then the next integral, since we're integrating with respect to x, can only involve z now. And then finally, the last integral has to be constants. So just keep that in mind.